Hi everyone, Mrs. V here, and today we are going to talk about amphiprotic substances. So let's get our whiteboard on and get straight to it. Amphiprotic substances are substances that can either donate or accept protons. So in order for this to occur, they must contain hydrogen. You can't donate hydrogen ions if you don't have any hydrogen. So you must have a hydrogen to donate. But also they must have some center of negative charge. So they either have a negative charge or they have some non-bonded electron pairs, and that's so that they can attract H+ to themselves. Now, of course, being able to donate a proton makes you a Bronsted-Lowry acid. And being able to accept a proton makes you a Bronsted-Lowry base. So the big question is, amphiprotic substances can do both. Are they acids or bases? Well, the short answer is that they are both acids and bases, but what we're really interested in is whether they can act as acids or bases in a given situation, not whether they are acids or bases. So it's, can they act as an acid, or can they act as a base? So because they are able to donate protons, they can act as an acid, so yes. And because they can accept protons, they can act as a base. So the actual answer is they're both. They're acids and they're bases. Looking at some examples, we can see all of the examples here: the hydrogen sulfate ion, the hydrogen carbonate ion, the hydrogen sulfide ion, the dihydrogen phosphate ion, the hydrogen phosphate ion. All of those fit those two criteria that we talked about. All of these have hydrogen, and all of them also have a negative charge. So all of those substances fit what we know as an amphiprotic substance. Now, what generally happens in tests or exams with amphiprotic substances is you're asked to write equations to show that a certain species is amphiprotic. And we do this by writing ionisation equations with water. So let's have a look here. Write equations to show that the hydrogen carbonate ion is amphiprotic. So in the first equation, we're going to show that it can donate a proton. So if the hydrogen carbonate ion donates a proton, then what will be left is the carbonate ion. And of course, the proton having been donated to the water means that we will also get a hydronium ion. So in that case, the hydrogen carbonate ion has acted as an acid. In the second equation, we need to show that it can accept a proton. So this time we need to take one of the hydrogens from the water molecule and transfer that onto the hydrogen carbonate ion, and that will make carbonic acid, H2CO3. And because the water has donated the proton to it, what will be left of the water is a hydroxide ion. So in this case, the hydrogen carbonate ion has acted as a base. But did you notice that in these examples, water also was acting as an acid and a base. In our first example, water has acted as a base. And in our second example, water has acted as an acid. So here we see water either donating or accepting protons. So yes, water is amphiprotic. And of course, if we draw the structure of water, we know that there are non-bonded pairs on the oxygen atom, and that is your center of negative charge that's able to attract the protons to it. And of course, water has 2 hydrogen atoms, so it has hydrogens to donate. Okay, your turn now. I want you to pause the video now and write equations to show that the hydrogen sulfide ion, HS-, is amphiprotic. We'll be back with the answer. Okay, how did you go? So HS-, let's react it with water. And we're going to show it acting as an acid. So it's going to donate a proton, which means what will be left is the sulfide ion. And we will form a hydronium ion. So here, HS- acts as an acid. And in the other equation, we're going to show it acting as a base. So this time it's going to accept a proton, which means we will make H2S, hydrogen sulfide, and a hydroxide ion. And in this case, HS- acts as a base. Did you get that one? Well done. Of course, the big question is, how do you know which of the 2 ionization equations will occur? How do you know if this substance in any given situation is going to act as an acid or a base? Well, what we actually have here is every amphiprotic substance has a certain acid strength. And it also has a certain base strength. Now, if you put it with a stronger acid than it is itself, it's going to act as a base. So if you react the amphiprotic substance with a stronger acid, then it will act as a base. And conversely, if you react it with a stronger base than it is itself, then it's going to act as an acid. So whether it is acting as an acid or a base will depend very much on what it's reacting with. You'll remember we talked earlier about water being amphiprotic. So water can actually react with itself in an ionization reaction. We have water reacting with itself. And one of the water molecules will be an acid and the other one will be a base. And we will get a hydronium ion and a hydroxide ion. Now, because of this reaction, every single substance that's dissolved in water, every aqueous solution, will contain some hydronium ions and some hydroxide ions. So that glass of water, your drink bottle of water that you drank the last time you played sport, that actually contained hydronium ions and hydroxide ions. Now, this reaction of water with itself only happens to a very, very, very small extent. And it has an equilibrium constant. You'll remember we talked about an equilibrium constant being a measure of how far a reaction had gone over toward the products in our previous video when we talked about strong and weak acids. So just a little bit about notation. We're going to use square brackets around a substance to indicate the concentration of it. So if you've got square brackets around HCl, that means concentration of HCl. So the equilibrium constant for the self-ionization of water is called Kw. All equilibrium constants are called K. There are some special ones. Ka is the acid constant, Kb is for bases, and Kw is for water. And Kw is found by multiplying the concentration of hydronium ions in your solution by the concentration of hydroxide ions. And it turns out that the product of those two concentrations is 10 to the minus 14 at 25 degrees. Believe it or not, water ionizes more or less depending on what the temperature is. Right, so now if we know every single aqueous solution contains hydronium ions and hydroxide ions, does that make every single aqueous solution an acid or a base? Well, not necessarily. It all depends on how much of each there is. So if you have a solution where you've got an equal number of hydronium ions and hydroxide ions, so the concentration of hydronium and hydroxide is equal, then we call that solution neutral. If you have a solution where there are more hydronium ions than hydroxide ions, so the concentration of hydronium is more than the concentration of hydroxide, then that is a solution that we say is acidic. And if you have a solution where you have less hydronium ions than hydroxide ions, that is, the concentration of hydroxide ions is greater, then we say that that solution is basic. Well, that's it for today. I hope you enjoyed learning about the term amphiprotic and amphiprotic substances. If you found that this video helped you understand, please consider giving the video a like. And as always, if you would like to learn more about this wonderful subject we call chemistry, please subscribe to my channel and watch more videos. I am going to see you guys in the next video.